Alright, so as I've stated before, part 7 is basically everything from part 6, just in a new context. So as a reminder, in part 6, we started by talking about the sampling distribution of a sample proportion. We were looking at p hat, our proportion from a sample, and we said as long as some conditions were true, p hat followed an approximate normal centered at the real p with a standard deviation of pq divided by n. And in part 7, we're going to be looking at a sample mean and what it's distributed with. Now, what I do want to point out here is one of the big differences in terms of telling part 6 and part 7 apart is when we're talking about a sample proportion, right? This was counting up the number of yes or number of successes within a sample, right? So in that case, we were dealing with a categorical variable. So our underlying variable here was categorical because we were looking at how many successes there were and the proportion of successes. Whereas if we're taking a mean, that means we're averaging things, right? Which means our underlying variable is quantitative. So that's the biggest difference here between 6 and 7 in terms of why we would do one versus the other. If we had a categorical variable, we can only use methods from part 6. If we had a quantitative variable, we can only use methods from part 7, which is why if you do the optional discussion board for this week, I have you do a confidence interval and hypothesis test for our categorical and then our quantitative variables. So our sampling distribution of sample mean, just to let us see what kind of happens. Here is a distribution that we know of a quantitative variable, right? The value on a die. So quantitative because there are 6 outcomes and they are all numeric, right? 1, 2, 3, 4, 5, or 6. We can even go ahead, make a cute little bar chart or histogram, and we can see this has a nice little uniform distribution. It's technically not the uniform distribution we saw back in part 5 because that was for a continuous variable, but it's a discrete uniform distribution. And then we can make a little table of all the different probabilities for these outcomes, and they're all equally likely, 1 out of 6. If we wanted to, we could then find the expected value and standard deviation, which would be the mean and standard deviation. The mean is simple enough. It should be, since it's nice and symmetric, at the halfway point. So that's going to be 3.5. But if I wanted to actually find this out, the easiest or simplest way to do your mean or standard deviation here, need to be able to move my Surface Pro. Okay, is that you could go back to what we did back in the day, set up all of our x's as L1, set up all of our probability of x's as L2. We could even use the formulas in that formula sheet, right? So the expected value would be all the x's times their probabilities, which would be 1 times 1/6 plus 2 times 1/6. But since we need standard deviation, the simplest thing would be to go ahead and use L1 and L2. So I've gone ahead and done just that. All of my x's are in L1, all of my probabilities are in L2. And then I can go back and do my 1-var stats using the values from L1 with the frequencies from L2. So you can see the mean is 3.5 and then our standard deviation 1.7078. Alright, so that has nothing to do with the sample mean. This is just the actual sample, an actual value from one pull. Alright, so if we want to consider the distribution of the average of 2 rolled dice, now we're looking at sampling 2 things and looking at an average. And therefore we could make a new distribution, right? In this case, the sums of all of our dice get anywhere from a 2, which is getting a 1 and a 1, to a 12, which means 6 and 6. Whereas something like a 3 is more likely than that because there's a 1 and a 2, or a 2 and a 1. So you can see all the different things, and we did this entire distribution out. In fact, you can go revisit the table from part 5. Yes, no, part 4, when we did the 2 dice. Alright, so in this case we're going to do the same thing. We're going to find the expected value and standard deviation, but this time we're going to find it for y, and this is a typo. We're going to find it for y, our average, because that's what we're looking to do. So, back to the table, and again, L1, L2. And this one's a bigger pain in the butt because obviously there are more values, but since our distribution is symmetric, the most likely thing is going to be our center. In fact, you could even go back to this little graph and sort of put each of these things in at their height. So 3.5 was the most likely. Obviously, I'm not going to go as tall as it's supposed to go. And then you went down slightly for the next, down slightly for the next. And it was possible to get out 6, right? But you're starting to see a symmetric unimodal distribution. And the standard deviation is slightly less, which makes sense because, well, we're now starting to get centered around this mean as opposed to being equally spread out around from everything. So what do you think will happen to this distribution if we took more dice? So instead of rolling 2, we took 3. So hopefully your prediction is thinking something like, well, it should be more clustered near around 3.5. which basically is a way of saying our standard deviation would go down. And we'd still expect to see it clustered around 3.5, right? That's the average, so we still want it centered at. And you might even be starting to think about maybe prediction that this will become more normal, right? We're not seeing normality on the first one because we're getting this thing looks like a pyramid. Maybe we'll start seeing true normality as things go on. So, that brings us to our first exercise, the sampling distribution of a sample mean. And this is a question I love to put on exams because it doesn't necessarily look as you might expect. So we have this distribution. Actually, let me break this up into a new video.